Swayam Prabha. Digital India. Educated India.
Hello dear students. So in today's class we will continue our discussion of obtaining the component equations of the momentum equation in spherical polar coordinates. Right. So in the last lecture we have seen what kind of geometry we should consider to get the change in the unit vector j following the motion. So we are in the process of arranging all the required terms to be able to write du by dt, right. So in that we have this kind of geometry. So you see here the j unit vector is pointing in this direction. So after this point travels a displacement of, let us say, delta x, which is here in the eastward direction, we will see that the j unit vector is no longer j, rather it is j plus delta j. Now in this figure it appears as if the vector, this vector is on the top of this vector, rather it is next to this vector. So the j vector is like this, the j plus delta j is in the same plane actually, that is what I want you to understand. So these three vectors are in the same plane, they are not away from each other, they are in the same plane, right. J has now become j plus delta j. Now we have to find out what is delta j, what is the magnitude of delta j and what is the direction of delta j. So in order to do this we will use some simple trigonometry. So this displacement, so omega is the angular velocity from this point to this point, right. So from this point to this point the distance is identified to be a by tan phi. So let us call this distance as x. Okay. Now using the simple trigonometry, so we can see that delta lambda is the angle. So what does it mean? It means that if this point P is in the beginning, then it is at a longitude of lambda here, and after it goes by a distance delta x, it will be at lambda plus delta lambda. So the change in the angle is nothing but delta lambda, right. Now r, so this is the radius of the earth is taken to be a, and this distance of the point P away from the axis of rotation is a cos phi. Fine. These are the things that we have at some point of time we have already used these kind of things, right. So using simple trigonometry we can write sin theta is equals to delta j by j. So where is theta identified? Yeah. So let us say we find the angle, this angle, we call this angle to be theta. So we can write sin theta is delta j by j. For very small angles we will write theta itself equal to delta j by j. So if we take the magnitude, we can write delta j, magnitude of delta j becomes simply equal to theta. Why? Because the magnitude of a unit vector is simply 1. Right. Now we talk about sin phi. Sin phi is a cos phi by x. Sin phi is equals to a cos phi by x. So this angle is phi, you see this angle, this angle is phi, right? So sin phi is a cos phi by x. So I am calling this as x. That means x can be written as a cos phi by sin phi, which is equals to a by tan phi, which is already kind of written there, right? Now delta j, using, let us say we call this as 1. Delta j, the magnitude of delta j was equal to sin theta, that is equals to delta x by a by tan phi, right? What is sin theta? We have already defined what is sin theta. Sin theta is delta x by a tan phi, this distance by this distance, right? So now we can divide these two expressions. We have one expression for delta j, which is equals to delta x by a by tan phi. So we can write delta j by delta x is equals to tan phi by a. Now from this figure we can, since j plus delta j, all of them are in the same plane, we can clearly see that the delta j is pointing exactly in the negative x direction, right? Negative x, that means which is in the negative I cap, right? So we can write here as minus I cap. Delta j by delta x is tan phi by a minus I cap. Just to see whether we have understood everything. So we have seen what is theta. Theta is the angle between j and j plus delta j. So we can write sin theta is equals to delta j by j. Theta is being a small angle, delta j by j. When we take a magnitude of delta j is simply equal to theta, because magnitude of unit vector is equals to 1. We leave it there. Then we come to sin phi. We write it in terms of the known quantities, which is a cos phi by x, and x turns out to be a by tan phi. So using these two, we can write delta j is equals to sin theta, which is equals to delta x by a by tan phi. So rearranging these two terms, pulling delta x into the denominator, we can write that delta j by delta x, the rate of change of j unit vector with respect to x, seems to have a magnitude of tan phi by a, and the direction seems to be in the negative x axis. That means I have put up minus I cap to denote the direction in which delta j is oriented, right? Like I said before, so d, if you want to find out d j cap by dt, it has to be a combination of dou j cap by dou x and dou j cap by dou y. Now we should also wonder what will happen to j. How will j change if there is northward motion? So far we have seen the eastward motion. How will the eastward motion influence delta j? Let us see how the northward motion will change the unit vector j. So now let us say, we consider the point to be here. That means let us say we have one point here, we have another point here. So now this point has a unit vector j in this direction. It changes to j plus delta j after this point moves from this to this, right? So this displacement, what is this? This is delta y, and this is phi at any moment, and this is phi plus delta phi at any moment, and this becomes delta phi, right? Now this is j and j plus delta j. This angle has to be delta phi again, right? And you will realize by simple vector addition that delta j will now point vertically downwards, right? And this vertically downward pointing vector is nothing but minus k cap, right? Now if I use simple trigonometry here again, I can write sin delta phi is equals to delta y by a, because this is a, right? So we are able to see for ourselves sin delta phi is equals to delta y opposite side by hypotenuse delta y by a. Right. So, the magnitude of delta y becomes a delta the same fact being repeated, right. Magnitude of delta y becomes a delta phi, and magnitude of delta j is equals to delta phi, which implies we can write dou j cap by dou y is simply minus 1 by a, and the direction seems to be in the k. Yeah. So, it is better that I put this minus inside this bracket just to denote that this minus is referring to the direction of delta j, right. So, this is minus 1 by a k cap. So, what have we got? We have got 1 dou x dou j by dou x, which will ultimately be written as dou j cap by dou x is equals to tan phi by a minus I cap, and dou j by dou y, which is equals to 1 by a minus k cap, right. Now, let us put these two things together. So, I have to write d j cap by dt, it has to be equal to dou j cap by dou x into dou x by dou t plus dou j cap by dou y into dou y by dt. Using the things that we have obtained, we can write dj cap by dt is equals to simply tan phi by a into dou x by dou t into minus I cap plus 1 by a dou y by dou t minus k cap, right. So, I can write dj cap by dt equals to u tan phi by a minus I cap plus v by a minus k cap, right. Just to have a sense of completion, we also write di by dt, which we have derived in the previous lecture. Di by dt was found out to be u by a cos phi into j cap sin phi minus k cap cos phi, right. So, using a similar kind of trigonometry, you can also try it yourself. We can also write dk cap by dt. dk cap by dt turns out to be, you can take it as an exercise, it is going to be very simple, and find out what is dk cap by dt. Now, so finally, we have these three expressions, these three rates of changes of unit vectors following the motion d I cap by dt, dj cap by dt and dk cap by dt. We are simply trying to write down what is du by dt. You have to remember, we started with writing the acceleration in a non-inertial frame of reference, then we ended up with the complete Navier-Stokes equation or the complete momentum equation. Now, we are now we are still not looking at the right hand side, we are still looking at the left hand side itself. That means, we are still trying to find out, see, you have this dou u by dou t, of course, then you have dou I by dou t, right. Now, we wanted to find out what is this. So, now we have expanded the left hand side, only left hand side, not the right hand side. In order to write the full momentum equation, we should better expand the right hand side also, right. Let us see how far we can get there, right. So, if I substitute all the terms that I have just into this equation, into this equation. So, I have to substitute this, of course, will remain like that, but these three terms are what we have derived right now. So, we will substitute those terms as well. So, let us see how it will look like. That means du, the rate of change of velocity in a non-inertial frame of reference will be I cap du by dt plus j cap dv by dt plus k cap dw by dt plus, and what I have done is, let us say I will write it as it is, u times u by a cos phi times j cap sin phi minus k cos phi plus v times minus u tan phi by a I minus v by a k cap plus w u by a I plus v by a j. Right. Now, what I can do is I can rearrange this equation by keeping the unit vectors as the multiples. That means, I am going to take the unit vectors as common and write the remaining terms within the brackets. That is going to be my LHS. The left hand side is all this. The right hand side is the sum of forces, which are again vectors. So, we need to resolve them, or we need to find out each of the forces components in the three directions, then we have to match the components, right. So, if I just substitute, if I just take the unit vectors as common factors, so I will write du by dt is equals to I cap right. So, just taking the unit vectors out, I have all the remaining other terms. Now, this is still the left hand side. The total derivative of velocity in a non-inertial frame of reference seems to have these three components, du by dt, dv by dt and dw by dt. Now, we have to think about the RHS. Now, all of this has to be equal to sum of forces. In this case, we have the PGF, the gravity plus Fr plus the Coriolis force plus the centrifugal force. Right. Now, for that purpose, what we have to do is, so we turn to component expansion of the force terms. So, this is the acceleration term, which is on the left hand side. Now, we have to component expansion is to be done on these terms. So, let us say we do that. Okay. The Coriolis force is expanded by noting that omega has no component parallel to I, the omega, the angular velocity vector, and its magnitude parallel to j and k. So, the omega's components parallel to j cap is equal to 2 omega cos phi and its component parallel to k cap is simply 2 omega sine phi. So, we can use the cross product and we can write 2 omega cross u as simply 2 omega times I j k 0 cos phi sin phi u v w, right. So, if we do this cross product, what we will end up with is minus 2 omega w cos phi minus 2 omega v sin phi along I cap minus 2 omega u sin phi along j cap plus 2 omega u cos phi along k cap, right. So, this is what is this? All of this is the Coriolis term. Now, let us look at the pressure gradient force. So, if we can expand, now ultimately I am getting the unit vectors out. So, so that I can compare all the multiples of unit vectors on the left hand side and the right hand side. So, the pressure gradient force is known to be, so how do you write the pressure gradient force is simply minus 1 by rho del P. Luckily, this is already in a easily identifiable vector form. So, I can write I times, if I am talking about unit mass, dou P by dou x plus, since it is a divergence, plus k cap. No, it is not a divergence, it is a gradient, dou P by dou z. It is a gradient term, right. So, it is a simple vector of dou P by dou x, dou P by dou y, and dou P by dou z. So, we have PGF, we have Coriolis force. Now, the gravity, which is in itself a combination of the gravity plus the centrifugal force, the gravity that is acting towards the center of the earth plus the centrifugal force which is actually pulling the object away from the axis of rotation, or which is acting perpendicular to the axis of rotation. We combine these two vectors and we call it as the effective gravity, which is of course in only one direction, right. So, it is in the negative z direction. So, that means it is minus k cap times the magnitude, let us say, okay. So, that is how much is the magnitude? 9.81 meters per second square, and the frictional term, this is the gravity, the frictional term Fr is equals to I Frx plus j cap Fry plus k cap Frz, right. So, what is this? This is the frictional force. Now, you will see, now we have all the scalars, let us say these are the scalars, the magnitudes. So, you put them up with the unit vectors, then you have the full vector. You have the, right, you have this scalar, you have all this scalars, right. Now, what you do is, what you can do is, you can compare the multiples of unit vectors on the left hand side and the right hand side. So, ideally, so all of this should be equal to sum of this plus this plus this plus this, right. So, if I do not write it all over again, rather I just compare the multiples of I cap, j cap, k cap on left hand side and right hand side, then I have the full momentum equations, or which we also call as the component equations. So, I will write them. So, by comparing the multiples of unit vectors I, j, k on either sides. So, one side you have the non-inertial derivative of velocity, on the other side you have all the forces, real plus apparent. So, if I do that, I will get the three momentum equations, which are actually the basic essence of all the atmospheric dynamics to to comprehend, right. So, they are the soul of this particular course actually, the momentum equations. They are the soul of the atmospheric dynamics, right. So, I will write these equations in its all full size or scale. So, they will look like this. So, I will write d u by dt minus u v tan phi by a plus u w by a is equals to minus 1 by rho dou b by dou x plus 2 omega v sin phi minus 2 omega w cos phi plus f r x. Right. So, these are the three component equations that I was talking about. So, this equation is called as the eastward momentum equation or the u momentum equation, because it is talking about du by dt, and this one is the northward momentum equation, or we can also call as the v momentum equation. This word, the third one is the upward, or more conveniently it is called as the vertical momentum equation or the z momentum equation, right. Now, you see these equations are a part of the governing equations. These equations combined with the continuity equation, thermodynamic energy equation, equation of state form the basis of understanding the atmospheric dynamics. So, if you want to understand how things move in atmosphere, you have to solve these equations. Now, interestingly, there are many features, there are many inferences that you can draw just by looking at this equation, just by looking at each of the term that appear in these equations. Let us say, so you see du by dt, dv by dt, dw by dt. So, the rate of change of velocity in the x direction is governed by this equation. For example, the rate of change of velocity in the vertical direction is governed by this equation, and this equation is the only equation where g appears, because g happens to have a magnitude of minus 9.81 only in the negative k cap direction. So, it is naturally obvious for it to appear only in this equation, right. So, you can draw all kind of inferences. So, you have different scalars of pressure gradient appearing. So, this is not a vector equation, this is a scalar equation. So, which is just trying to relate each of the scalar components in one particular direction, right. Now, this set of equation itself, they look complicated, but when you try to solve them, they are even more complicated. If you try to solve equation 1, you will find that in order to solve this equation, you will need v, or which you can get after solving the equation number 2. But when you go to solve equation number 2, you will find that you will need the information about u. That means these equations cannot be solved independently, they have to be solved simultaneously. So, you have to seek solutions u, v, w which are valid for all the three equations, right. So, it is not possible that first you obtain u, then you go ahead and find out v, then you go ahead and find out w. It is not like that, right. So, these three equations are called as the component equations in x, y and z directions, right. Now, then comes how do we put these equations to use. So, in the next class what I am going to tell you is these equations by now itself they are complicated. When we introduce what the full variation or full terms of this f rx, f ry and f rz, these equations look even more complicated, right. Then we will ask what is the relevance of these equations. Are these equations relevant everywhere, or is there a situation where these equations are relevant or a part of these equations is relevant, things like that, right. So, this is where we conclude. So, we say that we have derived these three equations, okay, these three component equations.